talk. So the title of my talk is Autonomous Robotic Assembly of Modular Space Structures. So this is really focused on an emerging kind of paradigm for space systems called broadly in-space servicing, assembly, and manufacturing. And this is really the idea of assembling spacecraft on orbit or assembling structures on the lunar surface, Mars surface, etc. Structures that are modular in nature, that have components that can be swapped out and upgraded over time, and also this enables you to build very large things that you couldn't fit in a single launch volume. So that's kind of the framing for what we've been up to here. And I want to start by talking about a specific application idea. So a few years back, around 2018 to 2019, there was this study led by JPL, involved plenty of other NASA folks, industry, academia, other government agencies, to look at the value proposition of an in-space assembled telescope. Like, so basically at what point is it worth it to assemble a large observatory on orbit as opposed to deploy the thing like a la James Webb with like all these complicated deployment steps. So the main takeaway from that study was if you want an aperture that's greater than 15 meters, that's when you would need to assemble it in space. And in fact, you could probably only ever get that by assembling the thing in space. So along the way of that study, they came up with this this conceptual design. Let's see if I can get my mouse on the screen. There we go. Yeah, so this is like a conceptual design that has this mirror over here supported by a backbone structure that reflects light down to instruments on this part of the spacecraft. So we here at Langley took this concept to a game-changing development program and generated a project called Precision Assembled Space Structures. And the goal of this project is to do a ground demonstration of assembly of the backbone structure for the mirror of that telescope. So this is an early simulation about how we might do that in a laboratory setting. We've also been building up this laboratory that's in this simulation here on center in building 1268, and the vision is that this will be a kind of a national capability to have this space equipped with robotics where we can do these full-scale assembly demonstrations for space structures. So what you're seeing in the video here are some industrial robotic manipulators, the kind that you'd see in like a automotive factory. These are basically our stand-in for any generic space robot. The real space robots look quite a bit different. They're not as stiff, not as high payload capability, but if we have something that's kind of over-designed, we can always augment the behavior of that system to simulate in hardware how any other kind of robot would operate. Okay, so we have a couple checkpoints along the way to that full-scale ground demonstration, and the first one that we call the phase 1 is assembling 3 modules, structural modules. So there are these, let's see, let me get the mouse over here again. Each of these is a module that we call a tri-truss because it's got a triangular face up at the top. And the mirrors for the telescope would sit on top of these. And yeah, that's how we build up the structure modularly. So to do this initial demonstration, there's this custom end effector that you see the robot going to pick up. That end effector is designed to grab onto these tri-truss modules. It's also got tools at each of those three ends of it to join the modules together. So there's like a screwdriver mechanism, there's some grippers. I'll show that up close later in the talk. We also have to plan motions for the robot to go equip that tool and then to go pick up the modules and then to bring the modules into their insertion points. And that's basically involves ensuring that the trajectories are collision free and dynamically feasible for the robot. We also care a lot about the uncertainties in the work site. So we have some a priori model of where these modules are stored, where they'd be stowed on the spacecraft for the real thing, and where the robot is mounted. But any kind of parameters like that are going to have some uncertainties, so we have to be robust to that. And that'll be a kind of a theme of the talk as well. Okay, the first kind of technical thing that I'm going to dive into is how we go about generating trajectories for the robot. The information that we provide is the end effector goal state. So that's where the end effector needs to end up, whether it's going to whether it's at the point where you grasp onto a stowed truss or the point where you go to insert a truss into the structure. It's basically just a 6 degree of freedom pose, and we provide our a priori planning scene. That is like a 3D mesh representation of where all the obstacles are in the environment. Oh, sorry. So we give that information to a path planner, in this case, a sample-based path planner. We're using a family of algorithms called RRT, which stands for Rapidly Exploring Random Trees. How those work is by randomly sampling robot states and checking if that state is valid, and then connecting that sampled state to a previously sampled state, and basically making a tree that you can eventually find a node in that tree that's within tolerance of that desired end effector state, and then you walk back through the path and you have a path that brings you from point A to point B. Okay, so the way that we do the validity checking is by using robot kinematics to propagate mesh representations of the robot links forward and check whether they're intersecting with obstacles. So once you have a path, then you also need to allocate time to it to turn it into a trajectory. And this basically involves looking at the dynamic constraints of the robot and scaling the time allocation of that path such that you don't violate maximum speed constraints, acceleration constraints, or load constraints on the robot. And then that becomes a command that you can send to the hardware. Just a little note about the planning scene. I kind of already touched on this. So we have a 3D mesh representation of obstacles. A real planning scene, a real environment for a robot can be dynamic and uncertain. So we have this a priori model, but it can be updated with sensor information. In particular, if you have a way to generate a point cloud, like a LiDAR attached to the robot or a stereo camera, you can combine that information with the a priori information. All right, there's a lot of math on this slide, but this is starting to talk about the robot kinematics. And the reason that I'm going into this is to show how we analyze uncertainty in the robot position, because the end effector has to go and pick stuff up, right? And you have to you have to get that end effector within some capture envelope of whatever you're going to interact with. And so we are using this Denevit-Hartenberg representation of robot kinematics. Basically, for each link in the robot, you can break it into 4 parameters, and then with those 4 parameters per link, you can describe where the end effector is going to be, or you can calculate where the end effector is going to be, and that gives you end effector pose as a function of link variables. And then if you had some distribution on those link variables, we're, the one that we're most care about is the variable that represents the joint angle. So what angle is your elbow at? Because that comes directly from a sensor reading, and all sensors have noise, right? So if you have a distribution of that noise, you can propagate that forward to this function and get getting the mouse over here. Sorry, can't really see it. Well, last bullet is showing how you can calculate a covariance matrix of the end effector variables as a function of the covariance of the joint variables. Basically, this is for if you're like at a given pose, small deviations will make this function behave linearly. I mean, that's kind of a basic thing with all nonlinear functions. They're linear about some very small region. So if your noise is small enough, then you can make these assumptions and kind of like a linear combination of things will get you that end effector covariance. Okay, so that covariance matrix lets you define an ellipsoid for the end effector with a certain confidence interval. So here I'm showing an example of a four-link manipulator up at the top with some specified covariance for the joint angles and the resulting end effector ellipse in the bottom. That's like zoomed in very far on the top image. Uh, so there, we could also use this this DH Denevit-Hartenberg model as a means of system identification. These are parameters that we can find from using system ID if we can take some measurements of the real robot. And if we're able to calculate that ellipsoid, that can be an additional validity check in the path planner. So I mentioned the idea, this concept of meeting a capture envelope. So you move robot into a position, you think you have the end effector in a certain XYZ roll pitch yaw, and it's got to be within some tolerance of the thing that you're going to interact with. And if your uncertainty ellipsoid is bigger than that capture envelope, then you should not consider that meeting the goal state and continue sampling in the path planner. That's the point I'm trying to make here. Okay, so all of this uncertainty stuff, we did some Monte Carlo analysis with this robot that I'm showing the picture is Universal Robots UR10. This is one of the robots that we work with in a smaller scale version of the testing. This is kind of just like a sanity check analysis. So we can get those Denevit-Hartenberg parameters for this robot, and for the joint angles, we're able to find the manufacturer reported uncertainty basically, and use that to do some Monte Carlo tests and get a distribution of end effector states. So these charts are showing for the pose shown on the right, on the left, XYZ roll pitch yaw of the end effector distributions about the mean. Kind of the takeaway here was we were just seeing like how accurate can we expect this robot to be, and we look at the standard deviations of each of these variables. 3 standard deviations would be a 99% confidence interval. So yeah, which one is X? So you know, we can get the robot within like a millimeter of where it needs to be. So that's pretty good. And we just did this for a couple different poses. Okay, another thing that we're doing here is we want to use multiple robots to do this ground demonstration. So the kind of the baseline concept is one robot is going to be responsible for retrieving tri-trusses from some stowed location, and this comes into play when we do the whole 20-meter structure, right? Because we need to be able to reach multiple places there. One robot retrieves the module and then hands it off to the robot that's going to install it. And so when they do this handoff, they have to come together, and there's two interfaces on the end effector. There's an infinite number of possible handoff poses that this could happen at, and we tried to find a way to pick the best pose to do this handoff. So what we came up with was the idea of minimizing uncertainty at the handoff pose. So we're looking at matrix properties of, or the properties of the norm of a matrix. This second line here gives us a bound for the uncertainty in end effector state. That's the Frobenius norm of the Jacobian of the robot, which is the partial derivative of end effector states with respect to joint states. So that gives us a cost function that we can minimize if we sum those together for both robots. Yeah, and there's some coordinate frames involved. This is what the handoff looks like. So we hand off the whole tool, the whole end effector. So essentially, there is this. Okay, I mentioned there's these two interfaces for where each robot can be connected at the same time. There's a known offset between those interfaces, and that shows up as a constraint in the optimization problem that I'm going to show on the next slide. Yeah, so looking in the bottom left of the slide, we can set up an optimization problem to find what is the best pose to do the handoff at. So the cost function is the sum of these Frobenius norms of the Jacobian of each robot. Note that the Jacobians are functions of the robot's joint variables, robot joint angles. And then their constraints. The constraints are that the two end effectors have that transformation offset that is defined by the two interfaces on the tool. It's a matrix norm instead of a vector norm. Here's the definition of it is kind of up here. So the definition is kind of the second line, norm of this vector. If you have a vector that's equal to the matrix times another vector, the norm of that vector is less than or equal to the Frobenius norm of the matrix times the norm of the second vector. And it's the square root of the trace of the matrix transpose times the matrix. Yeah, so that's just kind of some linear algebra stuff that's baked in.
I have a question.
Yeah.
So the concept here is that these are all like pre-planned path laid out. So the expectation is that robot A will do exactly this and robot B will do exactly this, and you're trying to minimize the pre-planned pathways to essentially perform this predetermined set of movements. Or do they have some like real-time feedback capability to realize, hey, it's a little bit off, but I can adjust my movement, using some sort of sensor feedback?
So we're doing, so the planning that I'm talking about right now is before execution. So it's not using feedback while they're running.
So you're expecting to basically choreograph everything from start to finish.
I mean, not quite. That's what I'm talking about here, but I'll have some stuff later on that will talk about how we correct using sensor feedback for, especially for when we get close up to where actions are going to happen. What we're talking about on this slide is how do we define the goal pose. So we're going to define this goal pose using the robot kinematics. Then we're going to plan a trajectory to that goal pose. And then when we execute that trajectory, that's where feedback control stuff.
And if you have two arms and you plan it so that this one this one can move and they can both safely move without hitting each other or hitting anything that the other one might be holding.
Yes. Yeah. Okay. That's kind of my my next slide. So yeah, so the way that this these operations are going to happen is we break the motion up into kind of gross motion and fine alignment. And so for the gross motion, that's what we've been talking about up until this point, where we plot a path from A to B, we just follow that path, and then that brings us close to the insertion point of the module or the point where we need to start grasping. And once we get to that point, we switch into a fine alignment mode, which is going to use feedback from a stereo camera. And the kind of architecture that we have here is for to use the stereo camera image, use just the RGB image from the camera, mask out the objects that we care about, and then use that mask to get a masked point cloud, and then register that point cloud against the CAD model to get 6 degree of freedom pose of parts that we want to interact with. So I'll get more into that in the next couple slides here.
Can I ask one more question real fast?
Absolutely.
So when you're talking about, the gross from A to B, is there some resolution in getting from A to B? Like, are the calculations done at like different points, or is it just considered one fluid motion effectively?
At the end of that process, it's one fluid motion. Like, so this is getting a little bit deeper into it, but so that first step, if you think back to that block diagram that I showed, that path planning step, that gives you just a sequence of waypoints essentially.
Yeah.
And then to allocate time to the path, we're turning that sequence of waypoints into a trajectory.
Okay, so you're using the constraints of the actual physical mechanisms to generate one dynamic motion within all the constraints across those waypoints.
Yeah, that's accurate.
Okay.
Okay, so to start thinking about the fine alignment stuff, here is what the ends of our grapple tool look like up close. So okay, this is where I'm gonna need to use the mouse. Okay, when we're going to insert a tri-truss into the structure, we need to bring it to the point where these fingers can close around this post. These fingers that are on an actuator. When the geometry of these parts is such that when these fingers are closed, everything is pulled in tight, and there's a bolt that gets driven to connect them. This is a screwdriver mechanism up here, basically. Yeah, so the accuracy that we need is the capture envelope of these fingers to this post. And this is just kind of a visualization of stuff I was talking about earlier, where we have the uncertainty ellipsoid of the robot, and we have the capture envelope, and we need to make sure that the uncertainty is bounded within that capture envelope. Okay, so this is our architecture for pose estimation. So we have stereo camera on the left-hand side. We take RGB image. We use do object detection using a mask RCNN kind of algorithm. That's a neural network that will detect which pixels in an image are part of a specific object. So in this case, we're looking for what we call the nodes of these truss modules. Those are the corners where the struts come together, because those are the parts that get connected. Once we mask out the object, we extract the relevant pixels and use those to generate 3D points with using the stereo camera. Basically, stereo camera basically gives us a point cloud, and it can map pixels in the image to points in the point cloud. So now we have this masked out point cloud. It's got none of the background junk. It's just the part that we care about. We can take the CAD model and line the two of them up. And because we know what the coordinate frame that the CAD model is defined in is, then we can get that full 6-degree of freedom pose of the object that we care about. So there's a lot of neural network stuff in that section, and we're doing training of that neural network with synthetic data. So we're rendering a bunch of images in Blender where we know the ground truth of what that pose is, so that we can have lots and lots of examples for training. But then the question is, how do we map the synthetically trained algorithm to real data? So we have some test rig that we're going to build where we can put parts into a few known discrete locations and basically verify that we get the same output as we would with synthetic data. Yeah, here's a picture of that test rig. So it's got the camera here on a slider. It's got the interface to mount the, oh, I'm using my sorry, I'm using my mouse on the screen that you guys can't see. Yeah, camera on a slider here. Part gets mounted here. This can rotate, and we also have some lights here. This would simulate lighting on the end of the robot, and this would simulate like the sun, for example, on orbit. I mean, we can move these around and check robustness to different lighting conditions. Okay, so here's kind of the good stuff. So this is our subscale version of the 3-module assembly. This is kind of what we're working up to right now. There's a couple jump cuts. That's where we're doing some of the fine alignment stuff. So in this version of the test, we don't have the pose estimation stuff in the loop. We have a manual fine alignment as a stand-in. Also, there's a few places where we need to update the robot's payload information when we grasp a module. So that's where the jump cuts are. Otherwise, this whole thing is like a 20-minute process. So there we bring truss 1 into alignments. We join it, and then we go get truss 2, which is I don't know if you guys can see truss 2 very well. It's kind of in the back over here. But yeah, this is in room 1178, building 1268. This is where we're building up a lot of this stuff. The end effector on here is a smaller version of the full scale end effector. I guess I haven't really talked about the scale. The big version of this, the tri-trusses, that triangular face is 2.8 meters, and these ones that we're assembling here are 1 meter. So it's about like a 1/3 scale. So the end effector that we built here has all the same actuators, electronics, and software as the full scale version. So we're using this kind of test to verify the software for that end effector. Just let it.
What's the what kind of horsepower, processing horsepower do you need right now to execute? I just reason I'm asking, I work in the electronics center and I have a background in FPGA design, and in my past life did like real-time machine learning on the edge type applications. And so I'm just curious, like when these things go to space, they're going to need to have some sort of processing capabilities that are
Yeah, or
able to execute in those types of harsh environments. I'm just curious as to what kind of horsepower you're using right now to potentially close the loop on these
so
machine learning neural network implementations.
yeah, so the machine learning stuff is running on desktop GPUs for us.
Yeah.
Yeah, the like the computational realizability of that stuff is definitely a question. Another you know, an alternative to running it on board though is to have some downlink and uplink. And if your operation is slow enough that you can do that, then I think we could still use those algorithms to generate inputs. And in our case, we use that pose estimation to do one update. It's not like a feedback loop that's running continuously. We bring it into where we think um, the fine alignment needs to start, and then we get a delta on the robot pose and then move in that direction. But I mean, yeah, it's an interesting thing for sure. It'll be interesting to see how it plays out with running stuff like that in situ. Okay, so I've got a couple charts that's just data from these tests. This just shows on the left shows the robot joint angles over time, the actual and the desired. The spot where there's like a bit of tracking error. Here, should have brought a laser pointer, I guess. Anyways, I'm looking at joint 3, the first section. There's a little bit of tracking error. That's where we switch the robot payload, and when we do that, mechanical brakes are engaged, which pulls everything a little bit off. The other thing to point out here is this kind of like chattering stuff in the roll angle on the right-hand side. The right-hand side, by the way, is XYZ roll pitch yaw of the end effector. That chattering is because we're at like a singularity and Euler angles. So we're just post-processing from a quaternion here, and it goes upside down to pick up the tritruss. So we've done 2 trials of this so far. Just data from 2 trials. We're eventually hoping to show high repeatability by doing like 10 consecutive trials. That's our goal. Some actuator data from when the joining happens. Yeah, I think we can kind of just go through this pretty quickly. Okay, here's another interesting thing that I haven't talked about yet. After we join tritrusses, we have the robot apply a test load to verify the connection. So this is data from the force torque sensor on the robot during that test load to show that load was applied, nothing broke. Okay, and what's up next for us is the full-scale version of this, and I didn't make this video autoplay. Hold on. This is our full-scale lab with the 2.8 meter tritruss and a larger industrial robot. And this video is just us checking it out. We just got the end effector mounted last week, and yeah, this is our first time manipulating the full payload with it. So this gives you a sense of the scale for what we're talking about. I know I just kind of threw numbers out there for the scale, but when you see it kind of next to a person, it's a little more impressive, I think, the capability that we're talking about with this lab that we've been building up through this project. So there's the tritruss on the test stand that we're going to join to. And yep. Okay, so that's pretty much it for me. You know, the summary here is we've demonstrated 3 module assembly at our 1 meter scale. That's what the fully assembled structure looks like. We've proved at least feasibility for our autonomous ConOps, validated some software that we created for the end effector, and we're hoping to do our full-scale version of this by the end of October. You know, barring any barring any extenuating circumstances. So yeah, that's it. I'm happy to take any questions.
Green. All right. Okay, so 15, I think you said that 15 meter for telescope aperture, 15 meter is when the benefit kicks in.
Yeah.
Is there any smaller point where the benefit becomes significant? What I'm worried is that, so if you're talking about 15 meters, that's such a big project that cannot afford to take the risk of a new approach like this, right? So I think we need to start something small. We need to demonstrate with something smaller, but unless there's benefit, smaller projects aren't going to want to use this either. So I think we need to.
So that's, I mean, it's a good point. There are benefits that kick in. It's just when you like do the whole cost analysis that they did in that study, that's the number that they came up with. But there's other benefits to the ISAM paradigm in addition to just being able to build large things. So if you have this, if you're able to build your telescope in a modular fashion, then you can go in and repair a lot more easily, because you can extract modules that are failed and replace them with new modules. You could also upgrade it over time. So there's no, actually one of the big problems in the ISAM world, if you will, right now is that there is not a cost modeling method that includes those kind of benefits for trying to like estimate the total cost of a mission. Like the fact that you can have a much longer lifetime, perhaps indefinite lifetime, if you can continuously replace components. So, you know, that's something to think about as well if anyone is in the position of deciding whether they want to build their spacecraft modularly. Let's see, the other thing was yeah, the size of the telescope. So yeah, I think my main point is there's other things besides just size that you can get from this.
Yeah, in terms of telescopes, I wrote a white paper to the Planetary Science Decadal Survey with Lynn Bowman and Bo Naz. And
oh, great.
I'm assuming that you work with them.
Yep.
So if you haven't seen a copy, I can send it. We captured what needs to be tested to demonstrate cost benefit at smaller scale. This is in the context of a telescope. So I know you guys can do some other bigger things too, but in terms of a telescope, we captured thoughts into what needs to be tested and what needs to be demonstrated. So I can share
that. I would love to see it. Yeah.
Sure.
Thanks. Yeah.
Yeah, I've got one from online and one from me. The one from online was the automotive industry does a lot of this kind of stuff, right? So what's unique about the research that you're doing here that's not just replicated in a BMW robot with a slightly different shape right now?
Yeah, what's unique here is that the environment is not as controlled, so uncertainties become a much bigger factor. So like in a assembly plants, you know where everything is. You can step in and fix things if if you have FOD in the way of the robot. On orbit, that's not going to be the case, so we have to build systems that are robust to that. That's the main difference, and I think the main theme that I try to hit on is yeah, being robust to uncertainties.
And then that feeds my second question, which is nice. So you were talking about 3 sigma mostly. So, that means 1 in 100, you're wrong. How many 1 in 100s can break it, basically? I mean, I guess if you're talking about something where you're talking about thousands of these if you're talking about assembling something massive, you're not talking about 20, motions, you're talking about hundreds to thousands to more. And then when you're talking about a 1% event, you're going to get plenty of them. It would seem like fault tolerancing this to the 1 in 10,000 would be I assume you have to kind of like build that slop into the joints where there can just, where 1 in 10,000, you're not off by more than 5 millimeters. And so the joints are 10 or whatever. And so you can just handle that. Is that the way that it's done?
Yes. Yeah. So I kind of tried to explain this, but maybe I don't have the best graphic, but okay. So that 99% that I talked about, I was using that for the end effector pose that you can calculate from sense to joint angles of the robot. Basically the takeaway there is you can use that to design a capture envelope for a object that you want to interact with. And in this case, we have these fingers. Where's my mouse? Been struggling with the mouse. These fingers grasp this post. We can use that analysis to size these fingers, right? So if there's probably a point where you can very easily make these fingers bigger than however many nines you want to go, right? So that's kind of the approach here is we use that kinematic analysis to inform design of mechanisms that are responsible for closing the last gap.
But then I guess it would follow into the design of the system. Like if you're talking about optics, right, you're ultimately trying to put that mirror to 50 nanometers or something, right?
Yeah,
And
yeah.
you're not putting anything to 50 nanometers with a robot, but whatever the tolerancing that you've kind of adapted your assemblage mechanism has to be tolerant to your positioning of the robotic system, which means the optics has to back out whatever. Let's say you end up placing it within 5 millimeters. That means the optic needs to go from 5 millimeters to 50 nanometers or whatever, right? So is that all that kind of like system analysis rolled up into these designs where it might be easier on one person, but if you kick the can but so hard into somebody else's world, then it becomes extremely expensive for them to fix?
Yeah. So
And I'll stop there.
I will say that these are considerations that definitely come up in the whole like development of this architecture, and the right approach is to spread the can out over all of the areas. But I mean that's maybe easier said than done. So this is something that really involves like communication between different sub teams on the design. But it seems possible to achieve based on what we've looked at so far.
So for this to be a feasible technology, like the James Webb and some of those other things, like, I mean, everybody was holding their breath for some of the deployment capabilities,
Right.
When different things were happening. And some of the magic that comes in integration for any kind of spacecraft is, I'm an electrical guy. So, how sensors are placed and wired and all those kinds of things is the capability. Do we feel like we have the capability in terms of building modular enough blocks that all of those complex things have kind of been positioned in such a place that these robots can pick up these pieces and then like these connectors? Does that increase the number of connectors where these like different intricate wirings and things like that make up the the passing of data and information from one part of the module potentially to another? Like what kind of capabilities do we have to ensure that those things get like
Yeah.
Not just
okay.
mechanically connected, but like electrically.
Yeah,
and-
the making electrical connections is definitely kind of like an open area for this kind of thing.
Because the more connectors you have, the more signal integrity issues you might have between communication links and those kinds of things. And sometimes there's just
Yeah, so
big
there's
downsides to making those modular.
right. So there's a trade-off to be looked at there because like I was trying to highlight before, what you get from this is the ability to swap out components to repair, to replace, to upgrade. And yeah, you may be introducing you're introducing connections that can be new failure modes, but you're also taking out deployment actuators that are other failure modes. I mean, the kind of the comparison to James Webb with the holding your breath for the deployment thing is if you're assembling a telescope in space and something goes wrong, you can send a backup module and put it in instead of losing the whole mission from a
Exactly.
deployment
no,
step
I
not working.
for sure.
So that's kind of the way that we think about it, and where the actual like dollar trade-off exists there, I don't know, but that's one thing that we're trying to
But I
figure
mean,
out as well.
that's going to be part of the analysis in determining modularity versus complexity.
For sure, and and that also goes back into that lack of cost models that can handle such a paradigm, and yeah, we're hoping that that's gonna be solved in the future. I mean, that's something that's being tracked by like the agency level ISAM team as a priority gap to fill. Is how do we model the cost of a ISAM system? Nick?
When you are calculating the uncertainty ellipsoid of the end effector, did you find that there were any linkage parameters that your system is particularly sensitive to? And then as you go from kind of the small 1 meter scale, lab scale, up to the full scale, do those sensitivities change at all?
So they do. It's totally going to be dependent on what the configuration of the robot is, and so yeah, so this is kind of like a made up example, but if the robot links are longer, you're going to be more sensitive to angular variations. So yeah, the idea there is to have really a piece of code that you can plug in those parameters to, and it can spit out here's what your ellipsoid is, and so we can run that many times for many configurations and make sure that the configuration that we have, the robot configuration that we have, can handle the tasks that we're giving it. Yeah.
I'm just curious. One of the main arguments seems to be, building a system like this really improves the robustness of, like a telescope in case, you've got a bad panel somewhere. I'm wondering if you've done it, if you've put any consideration towards robustness of the system, like to the robot itself. Like if the robot has a failure, is it like how well can it recover if it's got a bad gear or a bad actuator or something?
So that is yeah, that can be handled in a couple ways. I mean, yeah, well, if you have a robot that has redundant degrees of freedom, so basically if you have 7 degrees of freedom or more, then if you can detect that failure, you can lock that joint, and then you have a reduced range of motion, but you can still you can still operate. So that's kind of my favorite approach, just because it's like a fancy algorithmic thing. But I mean, you could also think of like having redundant robots in the work site, like having extra robots in the work site. I mean, the robot itself is like a module on the spacecraft that could be replaced and upgraded.
Do we have any? Oh, sorry. Well, I was just wondering, like, we have some of those robotic things coming out of like space shuttles. Do we have any data regarding like constraints that you put on these motors, like acceleration speeds and velocities? How different are those in space environments? Just in terms of, because I mean, you don't have gravity to like put friction on these extra gears, and all the weight becomes a non-issue.
So
Just curious.
So I will say I don't know what the load limits are for the space shuttle arm, but we do. I guess it doesn't matter what I'm showing on my slides. We've been doing a little bit of work on load constrained trajectory generation for this reason. I mean, basically, yeah, for sure the space robotic manipulators are way weaker than the industrial arms that we have in the lab. So we're looking at algorithms for generating the trajectory that include loads as a constraint. So we're really looking at model predictive control for that right now. The idea being that you first do your path planning, sample the sequence of waypoints, and then for connecting the waypoints, we use a model predictive control to generate that trajectory. That's what we're looking at right now. And same deal, kind of with the question about the robot having a failure and like locking that joint and reducing the workspace. You can carry bigger payloads if you know how that's going to affect the motors, the torque that the motors have to output. You can restrict the workspace such that you're not like carrying a big payload way out here. You can still manipulate that payload if you're holding it closer. So yeah, that's something that wasn't in this talk, but it's something that we're doing.